Quadratic formulas and graphs. Today we're going to move on to quadratic forms. If you're wondering what makes a form quadratic, I'll show you. It needs to be in this format. ax squared plus bx plus c is equal to 0. So one thing I want you to notice right off the bat here is that this form is equal to 0. There's nothing on the other side, so everything on the equation has been brought over to this side. And on this side of the equation, we see the appearance of x in two spots. There's an x squared here multiplied by a constant value a, and x to the first power, that's what we call the linear term, multiplied by a constant value b. It could be positive or negative, sometimes even 0. And then we have an additive term here, c, which also can be positive, negative, or 0. Okay? So let me show you some examples to get you used to the form. Let's say that we have 3x squared plus 4x is equal to 1. Is that the quadratic form? Not yet. That's right. We have to bring the 1 to the other side so that if we subtract 1 from both sides, we would have a minus 1 over there and then equal to 0. Okay, so keep in mind that you always want to bring everything to one side. Then you'll see that a is equal to 1, b is equal to 4, c is equal to minus 1. Okay, we're going to need to be able to recognize what the ABC values are when we get to the quadratic formula in another minute. Okay, so let me show you one more example which at first glance does not seem quadratic, but once you've simplified the expression and then brought everything over to one side, then you can see that it's quadratic. Okay, so let's say that we have a form like this. We got a bunch of fractions here. This is looking pretty complicated. So, like every time I see fractions, I'll just try to get rid of them and then see what the actual expression is without the fractions. Now, if you wanted to eliminate the fractions here, you'd have to multiply both sides by the least common denominator here, which is going to be this term, x times 3x plus 6. So let's multiply everything on both sides by that quantity. Over here you'll see that you'll get x, because you already have a 3x plus 6 on the bottom, you get the x there. Here this one already has an x, so you're going to get the 3 times 3x plus 6. And here this one has both, so you're just going to get 2x plus 6 like that. Does that look quadratic? Okay, so we're not done yet. Let's keep going. Here we have x squared plus x equals 9x plus 18 plus 2x plus 6. Okay, keep going with it. Combine all the terms on this side to get 11x plus 24. Okay, so now x squared plus x equals 11x plus 24. Then bring both of those terms over to this side to get x squared minus 10x minus 24 is equal to 0. Okay, does that look quadratic? Now finally it does. Remember, the form has to be equal to 0. So here the term a is equal to 1, b is equal to minus 10, and c is equal to minus 24. So keep in mind that you're going to want to carry the signs, like the minus on the minus 10 and likewise on the 24, carry those into the values of a, b, and c. Okay, so that's the quadratic form, and now I'll show you why it's so important to be able to recognize the numerical values for a, b, and c, because the number one thing that we're most interested in is going to be what solves this equation. When is this actually equal to 0? Okay, so the answer to that, the quadratic formula. Okay, the quadratic formula gives you the values of x that are going to solve this equation. And here it is. The values of x that solve it are minus b plus or minus the square root of b squared minus 4ac, that whole thing divided by 2a. Have you seen that before? Maybe, maybe not. Now let's just look at it for a minute and talk about what it means. Here you can see the appearance of the ABC. That's why it's very important to know all the values of those. And then you have this plus minus sign. What that's trying to tell you is that you could have possibly two different values of x that solve this equation. And that's inherently tied to the fact that you have an x squared. Remember, for linear forms, you only had one solution to a linear form, because it had just x to the 1. Now that we have the x to the 2, we can get possibly 2 real values for the roots. So these special values that are the solutions of the equation are also known as the roots of the equation, or the solutions of the equation, or some people call it the zeros, because it's the place where the equation will equal 0. Okay, so if you hear me say roots or zeros, it means the x values that solve this equation equals to 0. Okay, so let's try it out. You could do this for any quadratic you want. Even if the b or the c is equal to 0, it's still okay to do. The only thing you can't do it on is equations where you would divide by 0, so you can't use it when the a is 0. But look where the a is. The a is on the squared term. So if the a is 0, you don't need it because you actually have a linear equation. Okay, so you can use this pretty much for any quadratic. Let's have an example here. X squared minus 6x minus 6 is equal to 0. Okay, first thing you want to check, is it in the correct form? Yes, it's equal to 0. Okay, so now we can start to pick out what's the value of a, what's the value of b, and what's the value of c. I'll write it over here. A is equal to 1, b is equal to minus 6, c is equal to minus 6. Okay, and if we want to know the values of x such that that equation will equal to 0, then we just take the formula, and this formula would be given to you on a quiz or test in my class. You do not have to memorize it. But you do have to know how to plug and chug properly, and that can take a lot of practice depending on your comfort level with stuff like this. Okay, so let's check it out. Minus b. Okay, minus b. b is already minus 6. So minus b is a positive 6. Plus or minus the square root of b squared, so I'm going to square that minus 6, minus 4 times a times c, and that's a minus 6 as well. So the first thing I would say is watch out for all the minus signs everywhere. Okay, this is going to, yeah, don't forget about divided by 2 times a, so 2 times 1. Okay, so this is not an acceptable answer for your final answer. Okay, you have to work this out in a little more detail. So 6 plus or minus the square root, you see that's a 36, and that's plus 24. Okay, and it's all still divided by 2, and so we get 6 plus or minus the square root of 60 divided by 2. Okay, that's still not quite simple enough. We can simplify this a little bit more. 6 over 2 is 3. And the radical 60 right here, I'll just do a little side note. The radical square root of 60, that's the same thing as the square root of 4 times 15. Okay, now why would I write that? That square root of 60 is square root of 4 times 15. That's because I would be looking inside the radicals when I'm done. I will be looking for any factors that are a perfect square. And here, 4 is the perfect square of 2. And then that means that's the square root of 4 times the square root of 15. Okay, if you have the square root of a product of two numbers, that's equal to the product of the square roots. And here, that's why I was looking for this perfect square. You want to take any perfect squares outside the radical like that. So root 60 is actually equal to 2 root 15. And then this 2 would cancel with that divided by 2 there. So the final exact and simplified solution, there are 2 solutions, 3 plus the square root of 15 and 3 minus the square root of 15. There are going to be 2 values of x such that that equation right here is equal to 0. Then you can go to your calculator and you can get a decimal approximation to as many decimal places as you wish. But this is the exact and simplified form. I'll just write that. This is exact. And it's also simplified. So if you see that on a test from me, this exact simplified form, that is how I would be looking for it. Okay. Alright, so let's see. Why don't we try another one here? Quadratic formula. So I'll just leave that board up so you can see the quadratic formula. Sometimes this is going to give you 2 separate answers, as it just did in the last example. Sometimes, very rarely, but exactly sometimes, what's under the square root might turn out to be 0. in which case you only get one special solution, x equals minus b over 2a. We'll talk a little bit more about that when we discuss the graphs. And then sometimes the worst thing I guess that could happen is that if the thing under the square root is negative, then you don't get any real valued solutions at all. Okay, so let's go into an example of that. X squared minus 6x, oh sorry, that was the last one. Okay, so new example, 5w squared plus w plus 1 is equal to 0. Okay, now you can see that I've replaced the letter x with the letter w. That's because depending on different applications or word problems that you're in, you might be using a different variable, w, t, x, y, z. It's all the same as long as you have the square of it and then the linear term and then here the constant term. And you can still do it, okay? So then you want to make sure it's in the correct format and then start picking out these values for a, b, and c. These are called the coefficients. And then you would just apply the formula again. In this case, my variable is w. So w is going to be equal to minus 1 plus or minus the square root of 1 squared minus 4 times 5 times 1, all divided by 2 times 5. Okay? Alright, so that part still works out fine, but when we start to try to simplify this, that's when you can see the problem. This is minus 1 plus or minus the square root of 1 minus 20, so negative 19 all over 10, and you can't square root a negative number. You could square root it if it was a 0, that would be the special case where you just get the one solution if there was a 0 here. But negative numbers, you can't square root them at all, and so the answer is that there are no real valued solutions. So that means there are no real numbers w such that that equation holds. And so that is your official final answer, no real valued solutions. If you've studied math quite a bit, you might have heard of the imaginary numbers, which include the square root of minus 1 in their number set. So it does have two complex valued solutions, but no real valued solutions, which is what we're usually looking for in business applications. Okay, so are you getting the hang of this? Let's try it one more time. I'm going to write down an example, and I would like you to try pausing the video, applying the formula, and getting me the answer in its exact simplified format. Okay, so let's see. How about this example right here? Okay. Pause the video here and try to solve this one out, keeping in mind that you may first have to manipulate it in order to get it into that format that you need to pluck out the ABC. Okay, so you might have noticed this is not in the correct format yet, even though there's a square over here. You can't even just bring the 49 over. You're going to have to FOIL this out so that you can see what's the square term, linear term, and constant term. So the first thing you got to do is x squared plus 4x plus 4. And then you also want to subtract the 49 over there. So you get x squared plus 4x minus 45 equals to 0. And that's the form that you want to use. Okay, so then we'll just pick out the ABC. A is 1, B is 4, C is minus 45. Now if you want, you can use the quadratic formula again. C is a pretty big number. You might need a calculator to figure out all that. But another thing that you can actually do, something you might have learned before, is you could then refactor this. If you happen to notice that there's an easy way to factor this with integers, like let's think, the factors of 45, 9 times 5, right? Okay, so if I make it like this, x plus 9, x minus 5, you can see that 9 times minus 5 will be minus 45. And then when I add it, positive 9 minus 5, I get positive 4. So this is actually the factored form. So you could also factor. You can factor. You don't have to factor now, though. So just so you know, if you didn't see this and this is really hard for you to do, then you just take the ABC there, put it in the equation, and once you crunch out these numbers, you should get the same numbers. In this case, the solution was x is equal to minus 9 and positive 5. So those are the roots, those are the zeros, those are the solutions to this quadratic formula. And you can get it either by factoring or you can get it using the quadratic equation. Do you guys care? Is this meaningful to you? A lot of people would rather see a picture than this big honking formula right here. So let me just erase that for a little bit and move on to the topic of the graphs. Okay, so as I mentioned, you can have at most 2 distinct real-valued solutions. In special cases, you'll get 1 solution. Sometimes you'll get no solutions. What does this really mean? Do you guys know what this would look like if actually, instead of saying this equal to 0, I called this f of x, or I called it equal to y, and then I graphed it in the xy plane? You know what it looks like? It depends, right? It always looks like some sort of smiley thing. Either it could be up facing like this, or sometimes in the xy plane it could be down facing like that. Okay, so it's called a parabola. The graph of it's called a parabola, and it's going to be up. It's going to be a smiley one, so all right, smiley. And by that I mean up facing. I'll put the quotes around the smiley. Because the technical term is up facing if your parabola is going up in both directions over here on the sides. And this always happens when the term multiplying the x squared is greater than 0. Okay? And then you get the down facing or frown facing. I'll say frown. That's for down facing. You're going to get the down facing parabola if your squared constant a is less than 0. Okay, so we can have 2 different types, up facing and down facing, and they're both good. Let's look at the roots. Let's talk about what the roots look like. Do you know where to find the roots on the graph? Those are the places where the y equals 0. That's right. So y equals 0 would be right along this horizontal axis, also known as the x-intercepts. So the roots, also known as the zeros, or the solutions to this equals 0, are the x-intercepts. Okay, and now I'll show you how you can have the 3 different cases. There's 3 cases, and I'll use an up-facing parabola, but you could also use a down-facing parabola to illustrate this. This is the same whether a is greater or less than 0. We have the case of 2 real and distinct roots, and then we have 1 root, and actually when we do have 1 root, this is known as the double root because we only have 1 of it, but it kind of like comes out of it twice. And then we have no roots, and this is the case where algebraically you would see no solution, as I circled in one of the previous examples. Okay, so why don't you guys take a stab at it? Pause the video and try to draw the 3 different parabolas that you think I'm going to draw right now. And let's just use, without loss of generality, let's just use a is greater than 0. Okay, so if a is greater than 0, hopefully you knew to draw up-facing parabolas. And the roots are the x-intercepts. So if I have 2 real roots, that means it must have intercepted the x-axis in 2 real and distinct places. Okay? 1 double root, only 1 distinct root. What did you draw there? Maybe something like this, where it just touches the x-axis in just 1 special place, and that's it. That's when it just grazes the axis right there, and there's only that 1 single root. And then no roots at all? Well, if it's an up-facing parabola, then it must be always above the x-axis, never intersecting it at all. If I was using a is less than 0 and had a down-facing parabola, if there were no roots, it would always have to be below. There's no way I can draw a down-facing parabola that does not intersect the x-axis without it always being below. Okay? So those are the 3 cases. Graphically, you can see the roots. And then there's one other special thing that I need to talk about now in terms of the graph. And you can see, actually, let me leave this up for 1 more minute. The next thing that I want to talk about is the vertex. Okay, the vertex, you might have heard of it before. It's a very special place on a graph of a parabola, and it represents an optimal value. Okay, so the vertex is the optimal value And the word optimal can mean one or of two things. Either it means that it's the maximum value or that it's the minimum value, okay? And that actually still has to do with whether the A is greater than 0 or the A is less than 0. You can see here in the case where the A is greater than 0 and it's up facing, the vertex will be located right here. It's the minimum value, okay? So the vertex will be right here. I'm going to say vertex is the minimum. It's the lowest place that up-facing parabola will ever reach. In the case where x is less than 0 and you've got the down-facing parabola, the vertex located right there is going to be the maximum. That's the highest place that down-facing parabola will ever reach. Okay, so in either case, depending on what our function represents, we are usually pretty concerned about where the vertex is located and what height it reaches or it sinks to at the vertex. Okay, so I'll just give you the vertex formula. The vertex formula, it can be derived from the quadratic formula by taking the average of the two roots. So I'll just say one thing. The vertex is always located right in the middle of the two roots. Okay, so you can see it, the parabola is symmetric about its vertex. So if these are the two roots right here, if I took the average, that's where the vertex is always located. So if you want, you can take the average of the two roots from the quadratic formula to derive this. Or you could just write this down, or believe me, and when I assess you on a quiz or test, I will provide you with the x value for the location of the vertex, known as the vertex formula. Please note that this is an equation that gives you the value of x where the vertex occurs. Okay, so that means if this is the value of x right here, x is equal to minus b over 2a. Here's the value of x right here, x is equal to minus b over 2a. It gives you the x location, and then if you want to know the height, the y location, then you have to take that value of x and plug it back into the f of x, and then get the height. Okay? So the vertex formula here gives the x, but if it asks you for the vertex, where's the location of the vertex, you will say the vertex is located at an x value of minus b over 2a, and then the corresponding y value, which is a little hard for me to write down, not having the actual equation. So the x value is this, and the corresponding y value would just be applying that vertex x value into the function f of x, where the f of x is defined right here. Okay? So this is the vertex location as a point, and now I'll show you an example of how to locate the vertex. Alright, so let's just say that we have kind of a simple equation here. Let's say that we have, I don't know, x squared minus 2x plus 1 is equal to 0. Okay, this one is pretty easy. You could use the quadratic formula to find the roots if you wanted to, but right now we're not interested in the roots, we're interested in the vertex of this thing. So let's see, the vertex formula, I erased it, but the x location is minus b over 2a. So you see, it still requires us to recognize the a and the b, so make sure you have everything on that one side of the equation. And you can see the a here is 1, the b here minus 2, the c would be 1 if you wanted to use the quadratic formula. But right now, this tells us that the vertex is located at minus a minus 2, so that's a positive 2, divided by 1 times 2, so that's 2, so that's x equals 1. Okay, so the vertex is located at the x value, x equals 1, but I'm interested in something a little more than that. What is the y value for this? Okay, so let's see, how about I take the x equals 1 and plug it in for the y value. Okay, so that means I take 1, square it, minus 2 times 1 plus 1 is equal to 0. Looks like I got 1 minus 2 plus 1 is equal to 0. Okay, so that just means that the y, oh sorry, you don't need the equal 0 here. Sorry about that. I meant that this is equal to f of the value 1. Okay, it just turns out that the y value at this vertex is equal to 0 right here, so the actual vertex is located at the x value 1 and the y value 0. And keep in mind that when you're working with parabolas, it would be nice to show a graph of this. So you're going to want to practice with your graphing calculator and plug this in where you see the y equals function on your graphing calculator. This is the equation that you would plug in. Oh, sorry, I shouldn't have had this equal to 0. That was the lesson for using the quadratic formula. So when you're finding the vertex, actually, I guess it's good to have a mistake on the video, because that is a common mistake. When you're finding the vertex, you don't set it equal to 0 over there. You just use this equation, and then you recognize the a, b, and c, and then you plug it in, and you get the value, which just happened to be 0 for my case. Okay, so once again, when you're locating the vertex, you're going to use the vertex formula right here to get the x value, and then you're going to plug in the x value found into the quadratic equation to get the y value, and then you can answer as a point.